in Chapter 26, Quiz B, Question 1A. In Chapter 26, we're discussing the chi-square distribution. In this particular problem, we're talking about the chi-square goodness of fit test. There are three chi-square distributions that we'll be talking about. And again, in Question 1A, we're going to be talking about the goodness of fit test. Chi-square distribution is a distribution that helps us infer information about categorical data. So in Chapter 26, we're doing inference for categorical data. Here's a rough sketch of the chi-square distribution. You can clearly see that this distribution is not normal. And we're only going to be talking about this piece of the tail. Our p-value is here. And again, a low p-value means that we'll reject the null hypotheses. And a high p-value says we failed to reject the null hypotheses. The variable, I'm not sure if you could see it, it's quite small here. The variable for chi-squared is this Greek letter. It looks like an uppercase X in italics with the exponent 2. So that's the chi-squared distribution symbol. And you'll see that as we go throughout this video. Let's take a look at our prompt. In a local school, vending machines offer a range of drinks from juices to sports drinks. The purchasing agent thinks each type of drink is equally favored among the students buying drinks from the machines. The recent purchasing choices from the vending machines are shown in the table. So let's just take a look at the table. There were 159 lemon lime sports drinks recently purchased, 198 kiwi strawberry juice drinks recently purchased, 174 tropical punch drinks recently purchased, and 149 grape sports drinks recently purchased. That gives us a total of 680 recently purchased sports drinks. Okay, so you see here the steps for completing a chi-square procedure. Okay, so the first question is, or the first step is to find the expected values. Well, let's look at our prompt and see if we can figure out how we would do that. Test an appropriate hypotheses to decide if the purchasing agent is correct. Give statistical evidence to support your conclusion. Well, just a reminder, the purchasing agent thinks each type of drink is equally favored. Okay, well, if each type of drink was equally favored, then that would mean that we expect 25% of the 680 drinks to be in each flavor, right? So each flavor should represent 25% of 680. That would mean, let's see, take a minute, 25% times 680. That means we would expect 170 drinks, 170 purchases for each flavor. Okay, so that's our expected value. So step 1, find the expected values. We've done this. Check. Okay, we're going to go back to this chart throughout the problem. I'm now going to read the question. Test an appropriate hypotheses to decide if the purchasing agent is correct. Give statistical evidence to support your conclusion. Well, we want to know if the types of drinks are uniformly distributed, which means they're equally favored among the students. So our null hypotheses would be the types of drinks are equally favored among the students. The alternative hypotheses would be the types of drinks are not equally favored among the students. Okay, and here you can see that. Again, we have to check our conditions. There's a few new conditions with the chi-square distribution. The first one is the counted data condition. When we deal with chi-square distribution, we need counts, which means we need the number of lemon and lime sports drinks that were recently purchased and the number of lemon and lime sports drinks we expect to be purchased. And for those people who are following along, while I'm talking, you might want to put this information in list 1, 159, 198, 174, 149, and this information, the expected values, in list 2. Okay? So again, while I speak and talk about the conditions, if you could enter this data into list 1 and this data in list 2. Okay, so the next condition is the randomization. And we're not interested in making inference about other high schools, so we don't need to check randomization. Another new condition is the expected cell frequency. And the expected cell frequency is that we always expect values that are greater than 5 in each cell. This is considered to be a cell. And you can clearly look here and see that all of our cells are expected to be 5 or greater. Okay, so the expected cell frequency, the null hypothesis expects 25% of the 680 drinks, or 170, should occur in each flavor. These expected values are all greater than 5, so this condition is satisfied. So let's take a look at these conditions. The counted data condition, which is new for the chi-squared distribution. Chi-squared distribution always involves counts, okay? The randomization condition and the expected cell frequency condition. So under these conditions, the sampling distribution of the test statistic chi-squared with 4 minus 1, which is 3 degrees of freedom, we will perform a chi-square goodness of fit test. Okay, so degrees of freedom. In a chi-squared distribution, degrees of freedom is still given by the formula n minus 1, but in this case, n minus 1 talks about number of cells. And in our original data, we had 4 cells. So here, our degrees of freedom would be 3. Again, degrees of freedom is n minus 1, but in the chi-squared distribution, n represents number of cells. In our original data, we had 4 cells, so our degrees of freedom would be 4 minus 1, which is 3. Okay? So let's go up to step 2, compute the components. Okay, so I said we're going to constantly refer back to the steps of the chi-square procedure. Compute the components. Well, we're not really done with that, we're just starting it. But I'd like to take a look here. And here's the formula for the component. It's observed statistic minus expected value squared divided by the expected value. So I took the liberty of doing the first one with you. So 159, which was the observed value for lemon lime sports drink, take away 170, which is the expected number of lemon lime sports drinks consumed. We square the difference, and then we divide by 170. And when we do that, I think we get 121 divided by 170, which gives us 0.7117. Okay, so if you can just take a minute and make a third row in your table, and we're going to call that the chi-squared components. Okay, so just take a minute and find your chi-squared components. We know the component here is 0.7117, and I think I rounded 3 places after the decimal, so I wrote it as 0.712. All right, so here we go. Our chi-squared components for lemon and lime would be 0.712, for kiwi strawberry 4.612, for tropical punch 0.094, for grape sports drink 2.594. Those are the pieces of our chi-squared distribution. Okay, so now we're over here again. Find the sum of those components. That's the chi-square statistic. And you see the chi-square statistic, this formula right here, the chi-square statistic, is on your AP Stats formula sheet, so you know it's an important one. So let's take a look at that. The chi-square statistic is the sum of the individual components. So you're just adding 0.712 plus 4.612 plus 0.094 plus 2.594. That is our chi-square statistic. It's like a z statistic or a t statistic. Okay, let's take a look at that. Okay, and here we go. This is again the symbol for chi-squared. It looks like a capital X italicized with the exponent 2. Okay, and here's the formula, which you can find on the AP Statistics formula sheet. Observed value minus expected value squared divided by the expected value. And if you add up the individual components, you get a sum of 8.012. This is our chi-squared value, or our chi-squared statistic. A large chi-square value means lots of deviation from the hypothesized model. Therefore, we expect to get a small p-value. Okay, so let's take a minute and figure out how we'd get our p-value. Okay, so in our calculator, we're going to hit second vars and scroll down to our chi-squared cumulative density function. And it's just like a t-score. We need a lower bound, an upper bound, and a degrees of freedom. And again, degrees of freedom is n minus 1. And n represents a number of cells. In our original data, we had 4 cells, so our degrees of freedom would be 3. So again, taking a look at our distribution here, our chi-squared right here, this would be 8.012. Our upper bound would be some very large number, and our degrees of freedom would be 3. So take a minute in your calculator, enter those values, 8.012, comma, okay, and what you should get there is, you should get the probability of chi-squared being larger than 8.012, which is right here. That's the probability of chi-squared being larger than 8.012 is 0.0458. So that's a small p-value. It's less than an alpha level of 5%. So with the small p-value, we know we're going to reject our null hypotheses. Okay, so the p-value of 0.0458 is low. We're going to reject the null hypotheses, and we're going to say these data show evidence that the drink flavors are not uniformly chosen or equally favored by the students. Okay. So again, the p-value of 0.0458 is low, so we reject the null hypotheses. And these data show evidence that the drink flavors are not uniformly chosen or equally favored by the students. Okay, so I would like to give you some calculator shortcuts. That's what I have over here. I'd like to again go back up to our steps for the chi-square procedure. We found the expected value. We computed the components. We found the chi-square statistic. We now know the degrees of freedom. It's equal to the number of cells minus 1. And we tested our hypotheses. Testing the hypotheses means find a p-value. And we all know if the p-value is small, we reject the null. And if the p-value is large, we fail to reject the null. Okay, so let's go over some calculator shortcuts I thought you would enjoy. I asked you earlier to put these four numbers in list 1 and these four expected values in list 2. So here are my list 1 and my list 2. Okay, and then I'd like you to hit the stat key in your calculator. Stat key. You're going to arrow over to test because we're doing a hypotheses test. And if you scroll down, the test is called the chi-square GOF because it's the goodness of fit test. The chi-square GOF test. Okay, and if you hit enter, your screen should look like this. Okay, the chi-square GOF test. Our observed statistic is in fact in list 1. These are our observed values. Our expected statistic is in list 2. The degrees of freedom is n-1, where n represents the number of cells. And we're going to hit calculate. Okay, so hit enter. And our screen should now look like this. Our chi-squared of goodness of fit test gives us a chi-squared value of 8.012, which we got right here. That corresponds to our chi-square statistic when we did it the long way. It gives us our p-value of 0.045, which we know when the alpha level is not given, we assume an alpha level of 5%, and this number is less than 5%. So we're going to reject the null hypotheses. It tells us our degrees of freedom, and then it tells us this abbreviation stands for the individual chi-square components. And this is going to be important to us, so I want to take a look at this and how we can use this information to answer questions. Okay, so let's take a look at this a little bit further. Can everybody go back to their list? And now that we've made this calculation, we're going to go back to our list and we're going to go to list 3. And we're going to arrow up to the top of list 3 and we're going to hit second list and arrow down till we see capital CNTRB, just like this. Okay. And if we hit enter and enter again, we get something that looks like this in our calculator. I'm getting better, I'm not deleting the wrong things. Okay, and these are our individual components, and this is going to be very important to us in the next question. So just keep this in mind when we do question 1B. Okay, these are the individual components which we calculated earlier on in our problem. Okay, I hope I helped explain chi-square distribution. Again, they're used to infer or inference of categorical data. And in this particular problem, we did chi-square distribution for goodness of fit. We use the goodness of fit distribution when we have a one-way table or one categorical data.